I have a lot of ground to cover today, so let's move fast. 5 minutes, or maybe 3 minutes on the homework. Was it fair? Was it too hard? I've heard both versions. Too hard. I copied everything from your video. I mean, the functions. I am teaching this class. If I give you material, you can use it. If you have taken some of the functions from the video, good for you. I mean, it's. I haven't said that you couldn't do that. I actually told you a week in advance that was going to be the homework. But the idea is that in doing so, you're seeing the procedure to create a ground track. One thing. So this is the zip file. It's also in Canvas. I hope. I think it is. But anyways, it's on my website. So if you open these, there is the MATLAB part that pops up all those plots. There is also an SDK scenario that I created just for fun, because I had nothing better to do on the plane. And so people were looking at me like, what is this guy doing with the planet and stuff flying around? Yeah, that was fun. So basically what I do there is I create a spacecraft that starts at that date I gave you with the same orbital parameters, go for 15 hours, extract longitude and latitude, and then those two columns of data, I copied them into MATLAB and created the same plot, except I think SDK default gives you longitude between minus pi and pi. I asked to 0, 360, so you do a mod 360 and it will shift everything between 0 and 360. It's not a big deal. So I create basically the same exact plot from data that comes from SDK, which is pretty amazing. I think you guys don't realize that you are creating results that are given from commercial software, which I think it's pretty cool. But anyways, so the file is there, the scenario is there, but I thought, let's show the steps how I did it. So this additional video that I created this morning, I think it's 14 minutes. It's just me going on my screen and showing you how I created the SDK scenario and created an Excel file with the longitude and latitude, move that into a couple of variables in MATLAB, and plot the same plot. And actually copy-paste one plot on top of the other to show that they overlap. Okay? So just go through that. So that is my first lecture on SDK. Again, SDK is not a requirement. It's an additional tool. So here it is. Is audio working? This is a good test, actually. Let me see if it's working. It should work, right? Terrible voice. I don't want to hear it. Okay. Okay, yeah, just play this and watch the way I've done it. For those of you who haven't touched SDK yet, it's a good start. And then today we're going to finish maneuvers for now, at least for that chapter. Then we go back into maneuvering, looking at Gauss variational equations, the perturbation side of the house. But I will finish 2 impulsive maneuvers today. And this is really, from my point of view, covering all we need to know for now about continuous thrust. So everything we've done is I don't change the position, I change the velocity. That's impulsive maneuver. If you're going with continuous acceleration due to an engine that is always running and probably has a much smaller thrust, you just have to integrate the equations of motion. So what that means is that your equation of motion may be r double dot equals minus mu over r cubed r vector plus the thrust. And this is, of course, this to be dimensionally meaningful, this is thrust per unit mass. So first approximation, you can assume that the mass is not changing. You have a very efficient engine so that the fuel that goes out, it's very small over time, so you can assume it's constant, or you can model that changing. But anyways, what I'm asking you to do here as an uncollected homework, which you really should do though, is try these 3 cases. Go and open the same code you developed, or even the one I posted from homework 2. Remove everything that has to do with ground tracks. I don't care about that, or you can leave it there. And add now in the function with the equations of motion, relative acceleration with J2, add this additional piece. So what you have in that function is actually this now, right? You have plus some acceleration due to the oblateness of the planet, which we haven't explained yet, but it's there. So you're going to add this T, let's call it acceleration due to thrust, okay? You basically are going to add this piece. You just add another line into your code and see how it looks. And I play with those 3 cases. I'm going to post, as usual, the solution in a few days so you can see it and compare, but do it yourself. just have, for 15 hours again, a force in the first case of 0.001 meter squared, meter over square second, over second squared, I'm sorry, that is always pushing in the radial direction. What that means is you have planet here, the Earth is here, your satellite is here, this is the radial direction. That force, for some reason, is always pointing the same way, and it's of constant magnitude. So that's case 1. Case 2 is in the velocity direction. So this would be UR. This would be the unit vector in the velocity direction. And then case 3, it's always out of plane, so it will be pointing at you. And I play with those 3 numbers just because I need to find a combination that will show what happens. What you will see, and you may be able to intuitively explain that, is for case 2, for example, if you're always pushing with the velocity, you're increasing the velocity, right? You're increasing the speed. That is similar to what you've done for Hohmann transfers, for example, when you go to a bigger ellipse. So the effect of continuously pushing will give you a spiraling out type of orbit. You're increasing your energy all the time. If you're going positive with the velocity, you can change the sign of that and do negative, which is similar to what the drag force would do, for example, and the spiral would be going in. You're collapsing and going into the planet. You will see something very weird with the third case. If you are able to actually push against, well, in the direction of h at all times, you get an orbit that doesn't make sense, meaning that it's not really orbiting around the center of the planet. It's always lifted, which is not possible unless you're controlling all the time. Patrick, when we'll be ready to see what he has done, has worked on solar radiation pressure, and one of the applications for SRP that you can find in some of the research papers that we went through is basically taking the geobelt and lifting that orbit above the equator by having the sun continuously pushing on a solar sail. Some people say that it's feasible. So you can obtain a geostationary orbit, which is not at the equator, it's a little higher or lower, by constantly pushing in the direction of h, right? So you will actually see that in the case 3. And case 1, radial direction, that is very rarely done. It will give you some weird orbit, as you will see. It's not so intuitive to explain. But play with this, because this is what you have to do for continuous thrust. You integrate the equations of motion. Now, how do you design maneuvers with continuous thrust will be clear when we talk about the Gauss variational equations. There are differential equations for the orbital parameters A, E, I, little omega, big omega, in particular, that tell you how those quantities are changing if you have, in particular, radial accelerations due to thrust or something else in the velocity direction and in the h direction. So it will be clear then how you can play with everything that is non-Keplerian. Everything that we'll start next time, everything that is beyond this force model here, the oblateness of the planet, the fact that you're using an engine, the drag force, the solar radiation pressure, which is above LEO, and if you have reflective surfaces, does give you a momentum. Everything that is above Keplerian force is called a disturbance or / a control, because a control is a disturbance that you create, right? So we're going to deal with those when we start perturbations. But this really, for me, for now, closes the issue of continuous thrust. Go through this exercise and see what you get, because there is no intuitive way for now to really plan those maneuvers if we have continuous thrust. Questions? Comments on homework 2? No? So I want to show you one more thing. For those of you who have liked our Facebook page here, I just want to show you that if I'm not here teaching, it's because I'm doing something important that is job related. I became a member of this group here. The reason why I'm showing you this, well, it's important for my job. This is called the Aerospace Control and Guidance Systems Committee. This is a committee that has been out there for decades. Very small group of people, it's about 60. So in the meeting room will be more or less this number of people, maybe a little more. Not a standard conference type of group, but I've seen presentations about people testing the nozzles of the SLS, the new launch system for NASA, the nozzles and the actuators that control the direction of the force. I've seen amazing presentations, things that you usually don't see at real conference, regular conferences where I go to. So I'm pretty excited of being a member of these, which means that I have to do some work for them. Thank you. That's why I'm showing this. Continue. You need to continue. That's mainly the reason. Well, it's not to show off that I got this piece of paper. Believe me, remember these words. In a few years from now, I'm going to meet some of you at these events, at these conferences, and we'll be colleagues. Believe me, you guys, you have no idea how many people can understand orbits on this planet. It's just a few of us. It's just a handful of us. You think you're surrounded by them because this is your environment, but there's only a few people who can understand astrodynamics. And I'm sure that I will see some of you at these places, and that will be pretty cool. And I may be asking you for funding when I see you. You never know. You may become one of those who can give funding. Why not? That is the idea. That is when my job is done, when you guys know more than I do. Okay, so that's what I was doing. It was a quick trip, 3 days, back and forth. Don't do it. It's too short. So we need to finish a couple of maneuvers here. Maybe I'll turn on, I don't know. Can you see the board okay with the camera if I don't turn on the lights?
What's that?
These. You're liking the Facebook page?
Fine. Yeah.
Yeah, okay. So the first one is line of ups change. And I'm going to go quick on these two because we have all the ingredients to understand these maneuvers now. I just need to give you the, how it's done, how the delta V's are computed. That's all. And I'm not even going to try to represent that because it would be very messy if I do it by hands. But the idea is now we cannot do Hohmann. I have two ellipses. Believe me, this should be an ellipse, even though I think it looks like a circle. But anyways, it still applies. Where the line of ups is not the same anymore. So you cannot apply a delta V just at the apogee or perigee and go from an orbit to another. You need to find out if you want, for example, to go from orbit, do they have a name? Yeah. From orbit 2, which is this one with the line of ups inclined, and orbit 1, which is the one with the line of ups, which is horizontal for us. Well, if I want to go from 2 to 1, I can only do it where they intersect. We're still doing impulsive maneuvers. So impulsive maneuvers means that you can go from a type of trajectory to another type of trajectory only if they are touching each other, only if they share the same arc vector. And believe me, there is only two intersections that you can have between two ellipses. A good exercise that you can do, and I recommend you do, is take MATLAB, create an ellipse. I'm sure there is actually a command to do that. And then take that ellipse and rotate it. If you have the same exact ellipse, you will see there are two intersections. If you have a smaller ellipse, you still get only two. If you have a bigger ellipse, you have only two. This is the case where I believe P prime, which is the perigee of ellipse 2, is bigger than P, and you will have the two interceptions up there and down here. If instead P prime is smaller, the two interceptions will probably be down here somewhere. But again, you don't get more than two. And we actually have a solution for proving that. So say that we are given those two orbits. We know everything we want to know. So in particular, I'm going to use the eccentricities, E1 and E2, the angular momentum magnitudes, H1 and H2. And I do know, what do I know? I know the angle between the two. That's it. That eta angle between the line of ups. So before I can do a maneuver at the point I or J, doesn't matter, what I'm going to give you works for both points, well, I need to find out the intersection point, where they are. Because once I know where they are, I can figure out what the two velocities are and what the correction needs to be. Now you can imagine that it's not just changing the speed. Speed is magnitude of the velocity vector, by the way. So it's not just changing the speed, it is changing the velocity vector. As you can imagine, if I do it at I, the situation would be more or less like this. This is the planet Earth, or F, as it's called there, the focus. This is the point I where they intersect. I have this orbit 1 that goes like this, more or less, velocity 1. And the other one goes, I don't know, like this, velocity 2, right? What am I doing? It's the opposite. This is velocity 1, velocity 2. Doesn't matter. So if I want to go from this orbit to this one, this is my delta V now. Okay? Delta V vector. That's all you can do with impulsive maneuvers. You cannot take your time. You have to do it when you can, and it's an instant, and you fix the velocity. Whatever you need to do, you do it at once. So the one thing we need to find is where they intersect each other, and how do you do that? How would you find the intersection between two conics? What do you think? First of all, there is a relationship between those two angles, and that is the theta 2 is theta 1 minus eta, right? So once you find theta 1 or theta 2, you have the other one. What kind of equation would you set up to solve? Okay, the position of orbit 1 is h1 squared over mu 1 over 1 plus e1 cosine of theta 1, right? While the position on orbit 2 is given by a similar expression where here I have h2, or I have the same, but it's with, subscript 2. This is always true, right? So what happens at I or j? They are the same. It's the intersection. That's how you find the intersection, right? So you need to solve that equation in terms of theta 1 or theta 2. Again, they're not two variables. They are related to each other, so you can find one of the two. And this is where I'm going to skip the steps, because we do know trigonometry. We do know where to find solutions to trigonometric equations. We really don't need to prove too much. We just need to use them. So if you impose that equation, that those two expressions are the same, common denominator, etc., you do get something like this. E1 h2 squared cosine of theta 1 minus e2 h1 squared cosine of theta 2 is equal to h1 squared minus h2 squared. So basically, if I say that this expression is equal to this expression, if you don't mind, I'm going to erase what's in between here. Okay? Don't need this. This common denominator, removing the denominator, gives me this expression up here. Make sense? Nothing special. You can manipulate it so that, and you're going to believe me on this, it will look like this. I'll tell you what A is, cosine of theta 1 plus B sine of theta 1 equals to some C constant. And the things that we need to know are, can I erase this? Yes? That A is just a combination of those known variables as follows. I told you I do not care about the steps. I just need you to know how to find the delta V's. These are intermediate steps. Notice there that there is no theta 2, by the way. Because these are A, B, and C, and we have also used the fact that cosine of theta 1 minus eta, which is theta 2, where you see theta 2, you basically substitute this, and we know what this is, right? It's cosine theta 1 cosine eta plus sine, all sines. Anyways, all these, it's intermediate steps. Someone is asking you, you need to change the line of ups. The first step is, I need to find where I do it, meaning I need to find the theta 1. And again, that means finding also theta 2, because there is a constant between the two that I was given. And so it boils down, first step is this equation here, where again, A is known, it's a combination of variables that were given, B is known, C is known, everything is given. You need to find theta 1 from this equation. Yes?
How do you pronounce the fancy name?
Eta.
Eta?
That's how I pronounce it. Estimated time of arrival. Right? That's how I pronounce it. I don't know. There might be a better way. I didn't study Greek when I was in high school. I did Latin and I forgot everything. So it's an n. It's some kind of n. Okay? So how do you solve this? It's given. I'm going to give you the solution here. Now, how you find the solution, I'm going to just briefly mention it to you, and then if you don't believe me, you're more than welcome to go and refresh your trigonometry skills. C over A cosine of phi, where phi is the arctangent of this quantity here. Okay? So this is finding where they intersect. Theta 1. I'm looking at that point there.
Where are the little b, the little a, in that picture?
I'm sorry, the little b, the little a?
Are the a, b, and c invisible?
No. The a, b, and c are just combination of variables. It's just to make it easier for me. I could have left this thing multiplying cosine of theta 1, this thing multiplying cosine of theta 1, just to have this nicer. So the way this is solved, in case you don't remember, is a change of variable. I'm sure you've done this in some class. If you call cosine of the angle theta 1 x and sine of theta 1 y, x squared plus y squared is equal to 1. So it's basically finding the intersection of a line with the unity circle. You do all the steps, and you end up finding the solution. That's the solution, believe me. And there are two of them, of course, two intersections. If you're confused about where this is coming from, this is non-trigonometric. I'm not going to prove that to you. I don't need to. Just believe it. Any other questions? So, but this is just the beginning. I found where they intersect. What do I do with that? Now, this is where you should be able to tell me what to do. And I don't want, what is it? Yes?
So it says theta 1 on the board there, but it's also plus or minus.
Yeah, it's two
Is
solutions.
theta 1 both points of intersection, or is it just?
Yeah, it's this and this.
Okay.
Yeah, that's right, yeah. Just to prove again that it's two solutions. You get two intersections between two ellipses. Two circles, two ellipses, yeah. With a common focus, yeah. No. Theta 1 and theta 2 for point I. If you want to continue and locate point J, you will have to go with R the points down here, and there will be a new theta 1 and a new theta 2. They are still in the same relationship, which is theta 1 is theta 2 minus, or is it the other way? It's theta 2 is theta 1 minus eta. It's still the same relationship. That eta is given. It's the angle between the two lines of apses, and it's given. I'm trying to fix that. I'm trying to leave the orbit 1 and go on orbit, leave the orbit 2 and go on orbit 1, for example, or the other way around. It doesn't change the procedure. Okay, again, this is just math to get to that value. Once I am, can I erase this board? Once I am at that point, now you can start thinking about vectors, which is the part that you should be able to do. Now we're talking orbits. We're not talking about trigonometry anymore. Okay, what do you want to do? I need you to find, basically, let me see if I can zoom in again as I did there. This is your focus. This is your intersection. And that's orbit 2 that goes a little bit like this. And my velocity is like this, v2. And then I have orbit 1 that goes to the same point. And we'll have some other velocity. Okay? So I need to figure out those, right? Do we agree? If you have two velocities, two vectors, you just subtract them and find the delta v. How do you do that? These are memories from months ago. Well, I don't know if it's months. This point, maybe. Well, first, R1 is going to be h1 squared over mu 1 over 1 plus E1 cosine of theta 1. Now theta 1 is known, so you stick in whatever numbers you got from there, and you can do both at the same time. Actually, there is no analytical way I can show to say that that's better than that point down there in terms of delta V. I don't know that. So in general, you will have to compute the delta V's at both locations and just figure out which one is best. If you have the time to say that you find out that it's better to do it at J for the particular configuration you're given, if you have the time to wait until the satellite gets here, probably you do it at J. If you don't have the time and you have enough fuel to do it where it's more expensive, maybe you do it there. So it really depends. But you will have to do it for both. Okay, so that's my position. Well, I'm going to do 1 for the first orbit. What is the velocity? Remember this? So what is happening at that intersection is that it's the same radius. They are in the same plane. So my UR and my U perpendicular, they are the same for both orbits, right? Make sense? Okay, so I'm going to find the normal and tangential components of V1 and V2. What is V1? Perpendicular? No? Yes? Remember this one? No? Yes? I don't remember it. I know it exists somewhere. I have it here. And then I'm going to find the flight path angle, which you can also find like this if you want, or there is an alternative expression. That is a legit way to do it. So now I do have how V1, for example, is oriented with respect to, I have its magnitude, because of course the magnitude is going to be given from these two, right? Square root of V perpendicular plus, square root of V perpendicular squared plus V radial squared, that's your magnitude of V1. So from these two, you do know what V1 is in magnitude. Done. The speed, you know that. From these, you know also which way it's pointing. Because this is the flight path angle, right? It's defined as the elevation of your velocity vector with respect to the tangential direction. Remember? Okay, so you do this for orbit 1. Repeat for 2. Everywhere you see a 1, you're going to substitute a 2. So the velocity perpendicular for orbit 2 is h2 over r2, which is actually the same as r1 because this is happening at the same location. V radial 2 is going to be mu over h2 e2 sine of theta 2. Theta 2 and theta 1 are clearly related by that sketch there. And find the second flight path angle. You know, I think I can do it here. I do have a kind of a nice sketch that summarizes really what we are doing. Okay, my spacecraft is here. This is my tangential direction. In the end, doing that procedure, I'm going to find the magnitude of this vector V1 and its angle with respect to the normal direction. And the same for V2. This is trying to resemble that situation there. And this angle here, right? Is it too small? Maybe. Can you zoom? At least it'll be okay on video. Yeah. So I have found everything I need. I found the magnitude of the two velocities with this procedure repeated twice, and where they are pointing with respect to the common tangential direction. So I need to find the way to close that triangle. Do we see that? I'm going to zoom in even more. What did I call that? V2. This is the common U perpendicular direction. It's common to both of them. And this is gamma 2. And then I have V1. I'm exaggerating here. These are vectors. And I have the angle gamma 2 here. I need to find, I'm going to, from one to the other, it doesn't matter here. You're going to change the sign. Say that I'm going to, from V2 to V1. So this is my delta V. I need to find this vector. How do we do that? It's a triangle. So if you want the magnitude, which is really what we always want to compute fuel consumption, etc., it's going to be what? V1 squared plus V2 squared What do you do when you have two sides of a triangle and you have the angle between those? Because I do have the angle between V1 and V2. It's gamma 2 minus, this is gamma 1. is gamma 1 minus gamma 2, right?
Yes.
What is missing there? I knew I was going to run out of space. I knew it. So cosine gamma 1 minus gamma 2, right? Remember that? From somewhere? Yeah, geometry. Sounds right. Yeah. Okay, that's your delta V. End of the story. You do it twice, meaning if you want to figure out which point of the two is more convenient, I'm sorry, you have to do it for the other theta. Again, you have two values of theta 1 that you get from that. So this is the procedure. You're given two different orbits with a different line of ups. You know the difference between the lines because it's given by that angle. Assemble the A, B, and C as explained. These are your thetas. You need to figure out the velocities. You need to figure out the flight path angles. And that's all you need to tell me how much delta V you need to apply, which is, of course, not a pumping maneuver. I'm not accelerating any of the velocities. I'm actually adding a vector in some other direction. Make sense? Go open the book. After this sketch, there is an example. Go through that example yourself. There is nothing new here other than the fact that we're using some known trigonometry and that we're just playing with triangles. But there is really nothing new with respect to what we've done so far. You only do impulsive maneuvers when the orbits intersect. You cannot do it in any other point, of course. So this procedure is based on the fact that you need to find two interceptions and go from there. Any questions? Now this may be very expensive. Imagine that it could be possible. You're intersecting them at a point. Maybe they are two secure orbits. No, two secure orbits doesn't make sense. Well, maybe they are in such a way that intersection occurs where, imagine, the velocities are very similar. V1 and V2 are very similar. Now, the more you rotate the lines of ups, the more you're going to need a delta V, right? In principle. You know, and it may be, depending on this angle between the two, theta 1. So this angle here is not theta 1, gamma 1 minus gamma 2. If this becomes important, that delta V may be of the same order of magnitude of the initial velocities, the initial, given velocities, V1 or V2. So if you are in LEO and you're going at 7 kilometers per second at that point, or something like that, and for some reason you need to do a big change of line of ups with one impulse, this delta V may be in the same order of magnitude, 2 kilometers per second, and that's huge. That is most of your spacecraft. As go through your calculations of delta M again, and you will see that is a lot of your mass. Again, the space shuttle, I'm going to do very quickly the inclination change, was able to change inclination. The principle is the same. Now you're not only changing the speed, you're changing the direction of V. A change of plane is the same thing. You're going to create a delta V that is not in line with any of the velocities. The space shuttle could only do about 3-degree plane change, no more than that. Yes?
How reasonable is it to have refueling satellites or refueling spacecraft?
Yeah, I mean, people are thinking about doing that. So this idea of rendezvous and docking in orbit with autonomous spacecraft and servicing existing spacecraft with another one and refueling them, it kind of goes up and down. There are 10 years when everybody is doing that, and then they drop it, and then I've seen that, and then after 10 years, everybody is doing it again. I don't know why. DARPA had a long time ago a test on orbit where they would do autonomous docking with the idea that eventually you can go up there and refuel a satellite. Maybe a geostationary satellite that costs you several millions of dollars, and after 10 years you can use it for another 10 if you can refuel it. So at the moment, one of the biggest offices is at NASA Goddard. It's called the Spacecraft Servicing Capabilities Office, SSCO. They do develop exactly what you're asking. They have tools and refueling hoses for spacecraft. I think they have a plan to go and refuel a geostationary satellite. That's the last thing I knew about them. But again, going to a point in a given orbit, it still costs you money.
Right.
So it needs to be, the trade-off has to be advantageous, meaning that the satellite you're going to refuel and operate for many more years has to be so expensive that the cost of going there and refueling it, it's worth it. because we don't have fueling stations in space yet. That'll be cool. Yeah, yeah. But that's, that's something that, again, people have been talking about for a long time. Hubble, that Hubble, they had to change the lenses right after they put it into orbit. I was hoping to bring one of the astronauts who actually worked on Hubble and change the batteries, not the lenses. I know him, but it's too busy. But they have done it manually, so they had to repair that. So people are thinking about servicing spacecraft, be it changing a piece or refueling it. It is something we're talking about, but we don't do it on a regular basis yet. Everything has a cost. I think that SpaceX now, with this idea of landing rockets, if they can cut the costs down of going up there, then we can become pretty serious about refueling and servicing objects in space. Yeah, yeah. Because most of the mass, it's basically wasted just to get there. Okay, so let's do the inclination change. Same kind of approach, just the basics. What happens now? Well, now we're going out of the plane, and say that you are in the following situation, and I'm going to try to make sense here with this sketch, I hope. So this is a plane, okay, and here I have another plane. They don't need to be necessarily at 90 degrees as it looks like here, okay? So two planes that contain two different orbits, they intersect. Let's see, and so I have this orbit here, which is on this plane. Let's call this plane 1. And this other one here is plane 2. Okay, so this is my orbit on plane 1, and this will be the orbit on plane 2, right? Does it make sense? I am definitely improving. Yes, it could have been much worse. So I want to change. I want to go from plane 1 to plane 2, for example, whatever is the angle between the two. Again, it doesn't have to be 90 degrees. Actually, 90 degrees would be a crazy maneuver to do. It can be a few degrees, but I think it's easier to visualize. Again, it's impulsive maneuvers for the last time, so I can only do it where these orbits intersect each other. So it means either here or here. Now, if the orbit you want to, say that you are on plane 1, you want to move your orbit on plane 2, but the desired orbit is also much bigger, well then you will have to do it in steps. Because with an impulsive maneuver, you cannot go to an orbit that doesn't have intersection with your starting orbit, right? You first go to something that has an intersection with your original orbit, then maybe you do a Hohmann transfer once you are on plane 2. So bottom line, you either do it here or here when they intersect each other. Now, if you, again, do it in 3D, it's going to be pretty difficult, but what do they share now? This is my focus somewhere, right? My planet. And so the R is going either here or here. The only thing that now they have in common is the UR vector, not the U perpendicular. See that? So if I'm looking at what is happening from here, from a positive UR perspective, you should see something like this. Plane 1, plane 2, UR is looking at us, coming out of the board, and so the U perpendiculars now are not in common anymore. And say that the angle between the planes is some delta angle that I want to change. Again, if I go from 1 to 2 or 2 to 1, it doesn't matter. You're going to change the direction of the velocity of the delta V that you apply. So let's do this quickly. What is delta V? Is V2 minus V1. If I use the same kind of decomposition, radial, tangential, that I've used before, well, this can be expressed as V radial on second orbit minus V radial on first orbit times UR, because UR is in common. But then V perpendicular is not. V perpendicular 2, U perpendicular 2, plus V perpendicular 1. Is it plus or minus? It's a minus, of course. Minus U perpendicular 1. So that would be my delta V as a vector. And if you're asking yourself, how do I compute the UR and U perpendicular, go back to one of the first homeworks, where I asked you to integrate numerically the equations of motion and also do it non-numerically with the Kepler equation, where you have to figure out UR and U perpendicular. You've done it, so shouldn't be the issue here. Okay, well, how do you do delta V? Well, delta V squared, for example, you just do the dot product, right, for example, right? Delta V dotted with itself. Okay, well, it's going to look like the following. VR2 minus VR1 squared plus V perpendicular 1 squared plus V perpendicular 2 squared plus twice the product of the V perpendiculars and the dot product of these two guys, which you should be able to tell me what it is. Going to erase this side, okay? No. The title? Do we follow what I'm doing here? So I'm going to do the square root of that, and that's my general delta V. There is one more step. So I have expressed, up to this point, I have expressed the delta V as a vector using the radial direction, which again is common, and the two perpendicular directions, which you should have. You need to know the orbit you're coming from and the orbit you want to go to. So those you should be able to do. Now if I dot this vector with itself, it's going to be this first vector dotted with itself gives me this squared. And then remember that the URs and U perpendiculars are at 90 degrees. When you dot them, they give you all zeros. And then you get this dotted with itself gives you this dotted with itself give you, or the other way around anyways. This dotted with itself gives you the V perpendicular 1 squared and this V perpendicular 2 squared. Now when you dot these two, you don't get a 0 because in principle they're not at 90 degrees in general. And so you get this additional term. Agree? Okay. But that additional term, what is, I have two unit vectors. I know the angle between the two is theta. What is the dot product of those two? It's a scalar, right? What is it? It's the cosine of the angle, right? So, yeah, I don't think I need to erase this. My delta V, final delta V, is going to be the square root. I'm going to start the square root and close it when I think I'm done. VR squared minus 2 minus VR1 squared plus V perpendicular 1 squared plus V perpendicular 2 squared. I think, yeah, there is a minus, of course. Yeah, dot product between the two, there is a minus. Sorry. Otherwise, it doesn't come down to the triangle rule as well. 2V1 perpendicular, V2 perpendicular, cosine of the angle. So that's your delta V. If one is asking you go from plane 1 to plane 2, you need to figure out the radial velocities and the perpendicular velocities. Again, what we have done a long time ago with those radial and perpendicular expressions, it does pay off. So what do people do actually here? Well, they obviously want to minimize this delta V. You need to choose where to do it. Yes?
That angle is delta, correct?
Yeah. Does it look like a delta? Doesn't look like a delta? Bless you. Okay, so there's a few things that people actually do in practice. Now this can go, I think, right? No one really bothers about this. So you don't usually create a radial delta V. I want to make this as small as possible. So whatever it's under the square root, if I can remove it, it's a plus. So basically, if, you know, why would you do any radial change? You can change the plane without that, right? If the two orbits, now doing it in 3D is going to be fun here. But in general, these two orbits that are intersecting and they belong to different planes here, they may intersect here and may have a radial velocity which is different. So if you want to go exactly on the other one right away, you may need to add a VR, but that adds on the cost of that delta V. So basically, people don't do this. They just don't. It's policy. If you're going to change the plane, do that without the VR. So, okay, and that gives you that delta V. What else? How can you make whatever is left small? Now, this is a matter of the magnitudes of these, right? This is given. You can't really change these. It's the planes that you need to play with. So one is not radial. You don't do radial changes. The second is do it at apogee, if possible. Because one of the two velocities will be small, right? Possibly, if you're going from an apogee to a new apogee, they're both the minimum that you can get on the two orbits. Okay? In fact, if, let's see, if the apogees overlap of the two orbits, what happens? Actually, what happens is that you don't even have a VR. So the delta V is, you can forget about V perpendicular, that's actually V. V1 squared plus V2 squared minus 2 V1 V2 cosine of delta. What you're doing here is you're changing the plane, rotating about the line of ups. So basically, imagine that you're going from an orbit, which is an elliptical one, you just change its plane, and you keep it identical, right? And you do it at the apogee, that's what you get. Because at the apogee and perigee, there is no radial velocity component, okay? So if this happens, if you're fine with doing it at apogee and ending up in the identical, you know, an orbit that shares the same apogee, that's what you get. And then, if an additional case would be they are exactly identical, if V1 and V2 are exactly identical, I can erase this. Then your delta V, so this is the case that usually you see, is just this. You can prove that yourself. The one image I want to show you that is important. So again, the delta V you want to start from is, in general, this with the V perpendiculars. If you're doing it at apogee, which is probably a good idea, forget about the perpendicular and radial. It's just the velocity, because there is no radial component. If you're really going from the same orbit to a new same orbit on just on a different plane, this is what you get. And there is an important image that I left here for us to look at. Okay. So say in general that V1 and V2 don't have to be the same, but you know, they're different. I don't add any radial, of course. I'm just doing a change in the perpendicular velocity. There are two ways you can do it, right? You could do adding a rotating V1, just bringing it up here with this delta V, and then speeding up, right? Well, actually, there's three things you can do. You just do it all at once, add the delta V once and for all. The right delta V that brings the velocity at the right angle and with the right magnitude. So you do it with one burn. Or you do it with one burn that rotates V1 and then increases V1 and gives you V2. Or increase V1 first and then rotate. Right? Those are the three things you could do. Now, this sketch is there to show you that this is what you do. The delta V is the same. No, delta V is not the same. The end result is the same. You get a V2 at this angle delta. But why is this the best thing to do, which is basically doing it at the same time? Because the sum of two sides of a triangle is always bigger than the third one. So if I do this first delta V and that one, the addition of the two is greater than this one, which was this guy. If I do it this way, this and then that, it's still bigger than that, right? Because you could do all these things. You could think, hey, since I need to match that velocity to go on the new plane, not only rotate the velocity, but I also need to increase it in this case. Well, I could do it in several different ways. Well, that's the way to do it. You do it at once with one impulse. This covers, as far as I'm concerned, the impulsive maneuvers. That, the information that we need to know. There's more stuff in this chapter, but I think this covers pretty much the ground I wanted to cover. And I think we're done with time. I want to tell you there is an exam on Monday, and it's not here, just in case. And Tuesday we're going to Kennedy. How many think that they're going to go? No one. Yeah, 1, 2, 3. Okay. So we're leaving at 10 a.m., commuter lot, somewhere in there. I'm sure we'll find each other.
How
Yes.
long are we planning on being there?
As long as you want.
Like,
But I,
like food that I can get somewhere?
I'm sorry?
Food?
Oh yeah, they sell everything you want in that place if you have money. Yeah, oh yeah.